Our today's topic is differentiability. It is very important to go through the concept of differentiability because we have integration also in our syllabus. So what is a differentiability? The concept of differentiability has been introduced in the lower class. So the result is, we can say it as a definition also. Let f be a real function and c is a point in its domain. The derivative of f at c is defined as, we can say it as limit h tends to 0, and we have f c plus h minus fc upon h, provided limit exists. It is necessary that limit should exist. So it is equal to f dash c. Normally this dash, it represents that we are differentiating a function, or we can write it as that we have differentiate the function and we put the value of c. So we can write it as d over dx, or we can write it as f dash x over c. We can also write it as d over dx fx c. F dash x is defined as by this formula. So basically this is the formula for differentiation. Now we have every differentiable function is continuous. It is important that a differential function should be a continuous function. Now we have several algebra of differentiability. Number one is, let u and v be the function of x. So first thing is that u plus v, if we want to differentiate this equation, we can say q, it can be plus or minus, and we are differentiating the whole function. It hold a linearity property, means it will be u dash plus minus v dash. It comes like this, u dash plus minus v dash. Second thing is that if we have a product of two functions, how can we write it as u dash v plus v dash u? Means first we differentiate first function, second one is in the multiplication as it is, plus then differentiation of another function, and first function is as it is. This is also called a product rule. Then third, we have u upon v dash, means if we have a division, if two functions are in the division form, then we apply this rule. This will be u dash into v minus u v dash upon v square. Means differentiation of first function, another function is in the product as it is, minus first function as it is, and this time differentiation of another function, and in denominator we have the square of the second function. And it is, of course, it is necessary that v should not be equals to 0. Then we also have a derivative of composite function. Derivative of composite function. What is this? This is, let t be a real valued function which is composite of two functions u and v, that is f equals to v o u. We have two functions like this. V o u, put ux equals to t. What we have done? U equals to, we write it ux equals to t. What does it mean? If we put ux equals to t, that means f equals to v t. It means this thing. If ux equals to t, then f equals to v into t. Then we have df over dx. This we can say it's a formula. Df upon dx equals to dv upon dt into dt upon dx. It is the derivative of composite function. We'll apply wherever we find that there is a composite function. Composite function means that we have a function in the argument of any function. That is a derivative of composite function. Now we move toward an important rule that we apply for solving various numericals. That is called a chain rule. Chain rule. Let f be a real valued function which is composite function of u, v and w. That is f, w, o, v, u. This is chain rule. F, o, v, w into o, u. Now we have three functions together. So accordingly to the chain rule, we put ux equals to t. We put ux equals to t. Then we put vt equals to s and now if we put ux equals to t and vt equals to s, automatically f will be equal to ws. So accordingly, by substituting all this, what we have a conclusion? We have df upon dx, it's equal to dw upon ds into ds upon dt, and we have dt upon dx. So if we find any composite function, we can apply the chain rule. This is how we can solve this. Then there are various formulae where you can directly apply for the differentiation. For example, we have this is a symbol for differentiation. If we differentiate sin x, it will be equal to cos x. Then differentiation of cos x, it's equals to minus sin x. Then differentiation of tan x, it's equals to sec square x. Differentiation of sec x, it's equals to sec x tan x. There are many formulae for where we can apply directly for the differentiation, for doing the differentiation. Now moving toward the example. So example number 1, we have that we have to find the value of dy over dx. We have to find the value of dy over dx, and numerical is sin x square plus 5. Sin x square plus 5. So as we can see, it's look like a composite function because here it should be sin x. What we learn from the formula, we have differentiation of sin x only, but here it is given that sin x square plus 5 mean we have to do some extra work for this. Sin x square plus 5. So sin x square plus 5, we can solve it by applying the chain rule. Accordingly to the chain rule, we have y equals to sin x square plus 5. We can consider it as y equals to sin x square plus 5. For differentiation, because this should be x, so we consider it t equals to x square plus 5. So what y will become y equals to sin t. We consider we assume this value x square plus 5, it's equals to t. So we have y equals to sin t. Now accordingly to the chain rule, what we have to do, that the value of dy over dx, it will be dy upon dt into dt upon dx. What we have to do, we have to move toward these values. This is the main formula for the chain rule. dy over dx equals to dy upon dt into dt upon dx. From where we get this value? We get the value from the substitution. Y equals to sin t, that means differentiation of sin t is cos t. So we have dy over dt equals to cos t. And here we have what we consider t equals to x square plus 5. So accordingly, we have dt upon dx equals to 2x, because the formula of differentiation of x to the power n equals to n x to the power n minus 1. We apply this formula. X to the power n means x to the power 2. This will be equal to 2 into x to the power 2 minus 1, that is 2x. So, and the differentiation of a constant is always a 0. Any other formula we apply in this question is a constant. It's always 0. So because 5 is a constant, the value of 5 is 0 and x square is 2x. So I think we have all the values right now. dy upon dt is cos t, and into dt upon dx, that is 2x. But we have to notice one thing here, that the answer should be, because we are differentiating y with respect to x, so the answer should be in pure x. X means, so now we put the value of t that we consider at the starting of the question, t equals to x square plus 5. So t is x square plus 5 into 2x. So our answer is dy over dx equals to 2x into cos x square plus 5. So this is the way how we differentiate the whole function. So the value of dy over dx for sin x square plus 5 is equal to 2x into cos x square plus 5. Now we take another example. In another example we have cos sin x. Y equals to cos sin x. Again we have to find the value of dy over dx. So before finding dy over dx, let's consider the things, because we learn the formula for cos x only and here it is given cos sin x. Again we have to make some extra effort for solving this. So let t equals to sin x. So here the function will become y equals to cos t, t equals to sin x and y equals to cos t. And accordingly to for the formula we have dy over dx equals to dy over dt into dt over dx. So what we have here, y equals to minus sin t, and from here we have dt over dx equals to cos x. Putting the two values in our formula, dy upon dt is minus sin t and dt over dx is cos x. So we have minus sin, we put the value of t as we do in our earlier example, t equals to sin x into cos x. So this is our required answer. dy over dx equals to minus sin x into cos x. So this is the way how we solve the question, solve the example by using the chain rule. Now in other example we just have an equation. The equation which is given, that is 2x plus 3y equals to sin x. We have to solve this equation. Before solving the equation, the rule is that if we want to differentiate, we will differentiate both sides. So we have to find the value of dy by dx. So differentiating both sides. D over dx 2x plus 3y equals to d over dx sin x. Now it holds a kind of linearity property. We'll differentiate this then this. So if we differentiate 2x, 2 will come because the differentiation of x is 1. Then we have 3y, that will be 3 dy by dx. Because if we want to differentiate y with respect to x, what comes out? Dy over dx. And here we have differentiation of sin x equals to cos x. So the value of dy over dx is cos x, 2 will go there, it will be minus 2 upon 3. So the value of dy over dx equals to, for this equation, is cos x minus 2 upon 3. So this is the way how we solve the whole equation. Now in spite of sin x, if we take sin y, differentiating both sides first, we have to mention this statement. Differentiating both sides, what will come? D over dx 2x plus 3y equals to sin y. Now we have 2 plus 3 dy by dx. But now on the right hand side, what we see, in our early example we have sin x, but here we have sin y. Means the differentiation of sin y is cos y, but we have to differentiate y again. That will be dy over dx. Taking dy by dx on one side, we have dy by dx, it's cos y minus 3 equals to 2. So the value of dy by dx equals to 2 upon cos y minus 3. So this is how we differentiate our linear equation. Thank you.